Hi guys, my name is Mark, and in today's video we're going to be looking at question 11 of the higher level 2022 chemistry paper. This is going to be a multiple choice question, and let's get straight into it. So question 11 in this case is going to be a multiple choice question, and what you can read just kind of from the title here, I guess, is that we're asked to answer any two of the following parts. We have A, B, C, and D. So there's 4 parts to choose from, and we have to answer any two. And I highly encourage that you have a stab at answering all of them, because I mean it's going to maximize your chance of getting full marks. If you make a mistake somewhere accidentally, then they'll pick the ones that have like the most marks to give you the best chance. So in this case, we're going to move straight into question, or should I say part A, I guess, in this case. So having a look at part A here, there's going to be a few subparts. The first one we're going to be looking at here is part I. And what we're asked to do here is to define reduction in terms of, and then in part I we're asked to define reduction in terms of electron transfer. So what we have to do here is kind of give a definition, explaining what reduction is, but from the perspective of how electrons are moving and transferring around. And in part 2 and 3, they're more than likely going to ask us to define reduction in a few different perspectives. So in this case, we have to work with electrons. So for this question, the answer that is required to get you the full marks in this case is that reduction is the gain of electrons. And the way that I kind of remember this is by using the acronym, and I'll just write it down. So writing that out, that's what I've just kind of done over here. That's kind of just the shorthand way of me kind of remembering how to approach these questions. In this case, OILRIG, and there's all of the components of it. And we can now move on to the marking of this question. So for getting this first part correct, you're going to get a total of 4 marks, and that's going to be, it's going to be 4 marks for just saying that the gain of electrons is kind of how you define reduction when it comes to viewing reduction through the lens of electron transfer. So moving now on to part 2 here, we're still asked to define reduction, but in this case, instead of looking at through the lens of electron transfer, we're asked to look through how the change in oxidation number kind of manifests itself. And in this case, what we need to do is look at reduction and write down what's actually happening in terms of the oxidation number in this case. And the way that I remember this is that it's always the opposite of what's actually happening to the electrons. So it's actually nice and simple, because what we did in the previous question, we said, well, it's a gain of electrons. So in this case, it's going to be the opposite, is going to be the answer that we need for part 2 here. So as I was saying before, it's going to be the opposite of what is actually coming, like what's occurring for the electrons. So if we know that the electrons is going to be gained, in this case, reduction is defined as the decrease in that oxidation number. And just a nice and simple kind of answer here that's required, and there was a total of 3 marks going. So in this case it was 3 marks going, and that went for saying this key buzz term, which in this case is decrease, was the answer that you needed to get those 3 marks. So having a look now at part 3 here, we're going to be moving on to the next question. In this case, we're being asked, or should I say we're being told, that the oxidation number of hydrogen in most compounds is +1. So that's the first thing we're being told, and we're being asked, explain why the oxidation number of hydrogen in metal hydrides is -1. So this is a little bit more of a complicated question, and what I'm going to do is take you through that answer and explain kind of what's going on and the reasoning behind why oxygen, or should I say why hydrogen in this case, can have an oxidation number of -1 when it is in metal hydrides. So here is the answer that's required to get you the full marks, and I'm just going to go through it, kind of explaining what each bit of it means. The first thing that we're going to be seeing here is that hydrogen is actually more electronegative, so that's an important thing to note whilst approaching this question. Another thing that's being told here is that this is going to mean that it carries a negative charge, and like the -1 charge that we see in those metal hydrides. So basically, the key takeaway from this answer here is that hydrogen itself, it's going to be more electronegative, and it means that this results in it carrying a negative charge, especially when we see it here in these metal hydrides. Now, there's a few different ways you could approach this. We went down the path, should I say, of kind of talking about hydrogen and it being more electronegative. But you could also say that metals themselves are going to be a little bit less electronegative, and because they're a little less electronegative, they're more likely to form these kind of positive charges, which is why the hydrogen in this case can take on that negative charge. And similarly, there's a few other routes you could have gone with, but personally, I find this the easiest one to understand. And in this case, there was a total of 3 marks going for this answer. Those 3 marks are really going for this kind of sentence we had at the start, which is saying the hydrogen is more electronegative. So just to underline that, more is a key important term that you have to include here, more electronegative. And as I was saying earlier, you could also say the opposite, which is true, that metals are less electronegative, and this is going to kind of achieve the same goals. But personally, I just went for this way because it makes a little bit more sense to me. So having a look at part 4 here, we're going to be asked a question about oxidation numbers, and it's going to be actually a little calculation. In this case, we're told the oxidation number of oxygen in most compounds is -2. So that's oxygen's going to have a -2 oxidation number. And then what we're asked to do is kind of use this information to help us solve the next question, which is that what is the oxidation number of oxygen in OF2? So this is a specific compound, and what we have to do is kind of work with the information that we know to find the answer, which in this case is the oxidation number of oxygen. So the first thing to note is you might be just like, well, why isn't it just -2? Because that's what's mentioned kind of just up here. It says, well, in most compounds it is -2, and I'm sure they wouldn't actually ask us to find the oxidation number of oxygen if they give it to us already in the question. So in this case, we can expect it to be a little bit different. So the way that I'm going to approach this is by looking at it through the lens of the fluorine here, the F2. And we're going to use that to help solve this question. So an important thing to note here is that fluorine itself is going to have an oxidation number of -1. And the important thing to kind of take away from that is that it's -1 kind of all the time. And it's because it's an intensely electronegative atom. And another thing to note is that the total in this case, so just writing this down here, the total charge is going to have to equal to 0. And the reason that we know that is because this is going to be it's not going to be a charged or positively or negatively charged kind of species here. It's just OF2. It's going to be neutral. So it means that once we add up all the charges, it's going to have to equal to 0. So if we know that there's going to be 2 fluorines in here and they're both going to have a -1 charge, and we're also going to have a charge for oxygen, which I'm just going to call it in this case X, we know that once we add those all together, we should get an overall charge of 0. Now if we rearrange this to get X on its own, it means that X in this case is going to equal to +2. And for this question, the desired kind of answer you need to get here is that +2 charge, which kind of makes a little bit of sense once we look at it through fluorine. And similarly, like if you went ahead and were like, oh, well, it's just -2 because it tells us in the question, they're not going to really ask us to, find something that they've already given to us unless it's a little bit different. So in this case, that's kind of the reasoning behind how we got to this +2 charge. Now, for getting this answer correct, you get a total of 3 marks. So a nice handy 3 marks to pick up there. And once you've done a few of these, actually they become very easy to kind of spot and do them in your head almost, if you're lucky enough. So taking a look now at part 5, we're going to be moving on to probably the trickiest part of this question, which in this case, and if you just kind of read through it, it says that we have a following unbalanced equation, and it describes a reaction that occurs in an aqueous solution, and it's this big scary reaction here. And what we're told is what we're asked to do is to assign oxidation numbers and hence or otherwise balance this equation. That's the first thing that we have to do, and this is quite tricky, so I'm going to take my time once going through this, because even myself, I tend to forget and make little mistakes. So what we'll do is go through it nice and slow, and the first thing I'm going to do is draw out that reaction and the equation itself a little bit bigger so I can kind of work with it and begin assigning oxidation numbers. So now that I have drawn out our reaction just over here, I'll just kind of highlight it there. This is the big reaction and the equation, should I say, that describes that reaction. And what we're asked to do is first assign those oxidation numbers and then balance this equation. So what I'm going to do is go through it now piece by piece and assign some of the oxidation numbers. So starting from the left hand side, we're going to give this manganese here its oxidation number. In this case, it's going to be a +2. And the reason it's a +2 is because the oxidation number takes on the charge of the species on its own. So as we can see, it's going to be a Mn2+, so that means it's going to have a +2 oxidation number. Now looking over here at the second species, the BiO3 with a negative charge, it means that overall that is going to have a -1 charge. But what we already do know is that oxygens themselves, when they're not in associated with metals in particular, they carry a -2 charge. So what it's going to have is there's 3 of them, so it means it's going to be -6 charge associated with the oxygens, and we still have that Bi. And we don't know what that Bi is going to carry the charge, but we know overall the charge is going to be -1, which means that whatever Bi is, when we add that to that -6, we should get -1. And the required solution there, the required charge that you need for Bi in order to satisfy that is going to be a +5. And even if you just kind of look at it there, if we have a +5 charge in the Bi, and we have a -6 associated with the 3 oxygens in total, it means that +5 - 6 is going to give me -1, and that's this charge what we have up here. Having a look now at the hydrogen, similarly to the manganese at the start, it's going to have a +1 charge. And the reason for that, I'll just put brackets around the start one, there we go. The reason that it's going to be +1 is because it's going to just take the charge of the overall kind of ion in this case, and it's going to be H+, that means it's just going to be +1. Applying the same logic to the MnO4 minus here as we did to the BiO3 minus, each of those oxygens are going to carry a -2 charge, which means -2 times 4 is going to give me a -8. And what we need is the charge on the manganese is going to have to add to that -8 to give me that -1 charge. I'll just circle that again as well, that -1 charge there, which means the required answer here is going to be +7. And if you just add that 7 and -8, you'll get the -1 that you need to have for the charge overall. Looking now at this Bi3+, it's going to have the same rules as before. It's just going to take the charge of the ion because it's on its own, so it's going to be a 3+. And then looking at water here, the oxygen itself is going to carry that -2. And then we have two hydrogens, which means that they're going to carry a +2 charge, so +1 for each of those hydrogens. And because there's two, it's going to be +2 in total. And the reason that I know that is because it's going to be a neutral overall. And if we know the oxygen is -2, then the hydrogens have to add together to be +2 so that they cancel out to give 0. So now that we have kind of identified all of the oxidation numbers, we can start going ahead and seeing which ones are changing. And the reason that we're interested in which ones are changing is because that's going to tell us which kind of things are going to be oxidized and reduced, and we can use that to find other pieces of information like the oxidizing and reduction agents. And we can also use this to balance the equations. So the first thing to note here is that the manganese over here is going to actually, and I'll just write that out, it's going from this +2 charge, and it's going to actually change. It's actually changing to a +7. And where I'm getting that information from, it's just up here. That manganese can be 2+ there, and it's going to go to this manganese, which can be 7+ in this case. Overall, the manganese can have that 7+. So basically, there's going to be a change happening there, which is an important thing to note. And then the next one that's going to be changing is going to be the Bi, and that's going to be changing from this +5, and it's going to be changing now. And we look over here as well, so just highlight it also. The Bi here, which is going to be in that species there, and it's going to be going on its own over here on the right hand side. It's going to have a +3, and in that case, it's actually losing. It's going from +5 to +3. So what I'm going to do now is actually start drawing out some of the arrows connecting these two species together. So the manganese, I'm going to connect them together as well as the Bi. So in this case, manganese is going to connect with this manganese over here. And what we're seeing is it's going to go from this +2 all the way to this +7, and that's going to be a change of 5. So I'm just going to write in this little delta symbol, which in this case just means change. So delta is going to be a change of +5. Here we can look at the Bi, which in this case is going to go from here to over here, and it's going to be going from a +5 all the way down to a +3. And if we just do the same thing, the change, the delta is going to be a change of -2. So these changes in oxidation numbers, remember we were talking about them earlier on, if the oxidation number is going down, it basically means that the number of electrons being transferred is actually going up. So in this case, if we're losing, like in this top example up here, if there's going to be a delta of -2, a change of -2, it means it's going to be 2 electrons gain. So I'll just write that in. So gain of 2 electrons. And similarly down the bottom here, if the oxidation number is going to go up by 5, it means that there's actually going to be a loss of 5 electrons because they're the opposite of each other, remember? So there's going to be a loss of 5 electrons. And just to clarify, the shorthand here for electron being E with the -1 charge because electrons have a -1 charge. Now, the important thing to note here is that what is actually being oxidized and what's actually being reduced. Well, as we were talking about earlier, oxidation is going to be the loss of electrons according to OILRIG, which means it's going to be the increase in the oxidation number. So writing that down, this means that manganese here is going to be oxidized. I'm just going to write OX here for short, and then it means that Bi is going to be reduced because if manganese is being oxidized, then the other one has to be reduced. Now, similarly, at this time, I'd just like to write down a little bit of information about the agents in this case. So just to clarify what an oxidation agent and a reducing agent, I believe. An oxidizing agent is anything that causes, is substance that causes other things to be oxidized. And similarly, a reducing agent is going to cause other things to be reduced by itself being oxidized as well. Which means that basically, if you want to find the agent and the agent, what you do is find out what it is normally, and then the opposite is going to be its agent. So in this case, if manganese is going to be oxidized, that means it's going to be the reducing agent. I'll just write that down there. And then similarly, if the Bi here is going to be reduced normally, it means it's going to be the oxidizing agent. And I don't know if that's going to come in helpful later on or not, but this is just kind of the stage that I would do that because it's a little bit easier to kind of get out in front of what's actually going on. So now that we have had a look at what's going to be oxidized, what's going to be reduced, the agents associated with them, that's really, we've done a lot of good work here, but now what we have to do is actually go ahead and balance the equation. And the first thing to know here is that the change of electrons needs to stay the same, because we can't have a change in charge that's not balanced, because as everything in chemistry, everything has to be balanced. So what we're seeing actually up here, just this gain of 2 electrons, we're gaining 2 electrons, and down the bottom we're losing 5 electrons. So we need to balance those. And the way we're going to be doing that is coming to a lowest common denominator. Now the lowest common denominator between 5 and 2 is 10, and it can be found really easily just by multiplying 2 and 5. It means the lowest common denominator is going to be 10, so I'll just put that lowest common denominator, LCD. And it's important now that we use that lowest common denominator to balance these two numbers. So basically that 10, and I'll just draw a little line here separating our space here a wee bit. That 10 can be divided now by the gain of 2 electrons, and it's going to give us 5. And then similarly, if we divide that 10 by 5, it means that we're going to see a 2. So if we multiply this, up the top here, if we multiply that gain of electrons, those 2 electrons by 5, then we're going to have a gain of 10 electrons. And similarly, if we multiply this loss of 5 electrons by 2, we'll have a loss of 10 electrons. And that means that overall, we're going to see a little bit of balance, which is exactly what we need. And the way that we're going to accomplish that is we've already done the maths for it. All we have to do is multiply the Bi in this case by 5, so just going to be multiplying that by 5, and we're going to be multiplying the manganese by 2, and that's because we're using those charges to balance, and we've already figured out the numbers that we need to multiply by. So in this case you want to multiply that Bi by 5 because it's going to be gaining 2 electrons, so by multiplying the 5 electrons associated, or the 2 electrons should I say, associated with the Bi by 5, you'll have 10 electrons, which is exactly what we want. And similarly the same rules apply for the manganese. So redrawing out our equation here, just again, kind of nice and fresh, we have all that information from before, and I'm actually now going to put that in place. So what we said is that we need to multiply the Bi by 5 in order to balance the charges that way. So we're going to put a 5 here in front of the Bi, and similarly we need to put a 2 in front of the manganese, according to the equations that we had solved earlier. And now what we have to do is go ahead and start balancing what's on the left with what's on the right, and it'll allow us to make sure that the equation is nice and balanced. So just drawing a line down the middle, I'm going to just tally up what's on the left and what's on the right and balance the equation. So what we have already over here on the right is we're going to, or not even on the right, on the left, should I say, we're going to have these 2 manganese. And on the right hand side over here, we're going to just have 1 manganese, which means that we need to actually multiply this here by 2 in order to balance these. So we're going to put a 2 here in front of this manganese. Similarly, we can actually have a look now at our Bi. So on the left hand side, we're going to have just that 5. So it's going to be 1, and then we have 5 in front. So it's going to be 5 Bi's over there. And on the right hand side, we're just going to have Bi here, and it's going to be just the 1 Bi. And that means we need to multiply this over here on the right hand side also by 5 in order to balance that out nicely. So concluding that into our equation, we're going to have a big 5 in front of the Bi on the right hand side also. Having a look now at oxygens, we're going to have, just writing that down there, oxygens, there's going to be 3 inside of this species, and we're multiplying the whole thing by 5, and that means that we're going to have a 3 here, and then we're multiplying that by 5 to give us a total of 15, so just writing that out there. And then looking on to the right hand side here, we're going to have, just the first thing to note is there's going to be some oxygens associated with this MnO4-, and the first thing we have to do with that is we're going to have that 4 in there times the 2, and then we're also going to have, at the very end, we're going to have this water, which is really easy to forget because I always did it when I was studying for this. So we're going to have 1 oxygen there, which is going to give us a total of 9. So that's not obviously ideal. What we're going to try and do is try and change those number of oxygens to give us 15 on the right hand side also, because we need to have balance there. And the way that we're going to do that is we're actually going to be manipulating the number of oxygens in the water. And the reason for that is because we've already balanced the number in front of the MnO4-. So if we start changing that around, we're going to have to change loads of things. And that's not going to be fun for anyone involved. So what I'm going to do actually is I'm going to just rewrite this out. So it's going to be 4 times 2. And instead of going to have just that 1 there, what we need to do is we want to get to 15. So if we have 8 already and there's going to be 15, it means that we need to have a 7 here in order to get to our 15. And the way that that's going to manifest in the equation. There's going to be a big 7 in front of our water. And if you just kind of count over what's going on here, our manganese, should I say, is balanced, our Bi is balanced, and now our oxygen is balanced. Because what we can see over on the left-hand side is going to be 15 here. There's now going to be 8 in this MnO4, and there's also going to be now 7 in this water, so 8 plus 7 is going to give us the 15 that we need. Finally, we need to balance our hydrogen. So on the left-hand side, we're going to have hydrogen, and there's going to be just the 1. And then on the right-hand side, how many hydrogens we're going to have? We're going to have this 7 times 2 coming from the water. So it's going to be 14 hydrogens, which is a lot. So 7 times 2 there. And what we need to do is just balance the left-hand side. It's much easier to balance the left-hand side this time, because if we start changing stuff on the right-hand side, we're going to end up having to change everything again. So what I'm going to do over here on the left-hand side is multiply this by 14, and that's going to manifest as a big 14 in front of the H plus there. And it means that overall we're going to have a nice and balanced equation. Now over here on the right hand side, just kind of like in a little box, what I'm going to do is just verify that we've gotten it all right. And what I'm going to do is add up all the charges and make sure that they equal on both sides. So the first thing we're going to have is on the left hand side, so LHS just stands for left hand side. We're going to have 2 times A plus 2, and then we're going to have plus 5 times a minus 1, and then we're going to have plus 14 times a plus 1, and we can add those together now in a minute. And then on the right hand side, so RHS stands for right hand side, what we're going to have is a 2 times a minus 1, and we're going to have a plus 5 times a plus 3, and then we're going to have plus 7 times 0. I'll just draw like kind of like a dotted line in the middle so we don't get confused. And what we're going to do is just add these all together, and hopefully we get the same number. So on the left hand side, if we add up all of our charges, we're going to get to a number of plus 13. And similarly, if we add up all the charges on the right hand side, we're going to get to a number of plus 13. And because the number of charges on both sides is balanced, and also all of the there's going to be the same number of everything here on the left and the right hand side, means that the whole equation is now balanced. So this equation, I'll just put a little asterisk beside it now, including all of the numbers in front of it, is now perfectly balanced. So coming back to the start of the question here and looking at all of the oxidation numbers involved, when it comes to the marking, the breakdown was fairly simple. There was a total of 9 marks going in this case, and the marks went as follows. You got 3 marks over here for getting the oxidation numbers correct for the manganese. In this case, we're going to have a plus 2, and also, and sorry for just kind of drawing across myself here, the plus 7 over here is going to give you another 3 marks. And then similarly, you're going to get another 3 marks for getting the oxidation numbers on your Bi, which is going to be the plus 3 over here, and yet again, just drawing over myself, the plus 5 over here on the left hand side. Finally, the last 3 marks give us our total of 9. It's just going to come from getting the whole thing correct, which in this case is 2 Mn2 plus 5 BiO3 minus plus 14 H plus with a little arrow there, and it's going to go to 2 MnO4 minus plus 5 Bi3 plus 7 H2O. So it's a big mouthful, but in this case, we have successfully balanced the equation. So finally, we're moving on to part 6, and in this case, we're asked, identify the reducing agent in the reaction above. So thankfully, we've already actually done that, which was just kind of a step that we were doing anyway. We've actually already done that. So what we're going to do is just copy in the answer that we got from above to our answer box here. So if we recall from the previous balancing equation part of the question, we found out that Mn is going to be the reducing agent. So in this case, Mn is the reducing agent, and this kind of 2 in the brackets in this case is just showing that the charge overall was plus 2 at the start. Now you could also write kind of Mn in any part of it, but as long as the examiner understands that you know that manganese in this case was the reducing agent, then all is well. And for getting this thing right, there was a total of 3 marks going, and you got those 3 marks for just getting your manganese correct in this case. So now moving on to part B here, we're going to be moving on to a different kind of subsection of the multiple choice question. And in this case, part B is going to be asking us a little bit about, it seems to be ethanol in this question. So a few drops of oxidizing reagent were added to 0.5 centimeters cubed of a sample of ethanol. And there's a little formula beside it, and this was done so in a test tube. And they're being asked what was observed when the oxidizing agent used was, and moving on to part I here, was a warm dilute acidified KMnO4. So basically what we're seeing here is we have some warm dilute acidified KMnO4 being added to some ethanol and being asked what's actually going to happen here. So yeah, let's get straight into the answer. So in this case, the required solution to get you the full marks was that a colour change of purple to colourless is what was observed. And in this case, basically that purple, or you could also, dress this up as kind of something like pink or violet also would suffice. In this case, is going to go from that kind of bright pinkish purple violet colour to a colourless. And you could also say that it decolorizes. Either of these is sufficient. And this is the easiest way to get your full marks here. There was actually an amazing 6 marks going for this question, so you just got 6 marks here for a very simple colour change, and that's actually quite a lot of marks for what in this case is basically just one line. So definitely worth doing this question. So having a look now at part 2, we're going to be asked, we're being asked, kind of building off from the last question, what's actually going to happen, what is observed when we add this reagent to the ethanol. In this case, the reagent that we're looking at is Feeling's reagent, and we're also told it is preheated to about 40 degrees. So what we're going to be seeing here is another colour change. So it's important to state what's going to happen before, the colour before, should I say, and then the colour afterwards to get your full marks. So for this question, the required solution to get you the full marks, in this case, it was a colour change of a blue to a brick red precipitate. And you could also in here mention another term, which would be, instead of precipitate, you could say solid. But either way, the important thing to know here is that there was a change of colour from a blue solution, if you will, to this brick red precipitate. Now, you don't need to include the term brick red, you could just say red, but I just tend to kind of get in the habit of saying it because it's a little bit more easy to remember, because brick red stands out a little bit more than just, I guess, normal red. But in this case, another nice simple question that is just a colour change. And for getting this colour change right, you got a total of 3 marks, which was just kind of associated with this brick red part precipitate as well. It's important to include, but either way, a nice 3 marks to pick up. So having a look now at part 3, what we're going to be asked to do is identify the organic compound that is, formed as a result of the oxidation of ethanol using these 3 agents. So what we're going to be doing is we're going to be oxidizing ethanol, and we're kind of being asked what's going to come about as a result of this. What I'm going to do here is I'm going to draw out actually, the kind of the chemicals themselves and their structures, and kind of talk about what's actually happening piece by piece. So in the case of ethanol, which is kind of described here with the structure on the left-hand side, when we mix it with these other agents that we were mentioning earlier, what's actually happening is we're going to be oxidizing it, and we're actually going to be introducing this oxygen here as well. And as a result of adding this oxygen on, what's going to happen is this compound over here on the right is going to be formed, which is hopefully something that's a little bit more familiar to you. And in this case, what actually we see being formed is ethanoic acid. And how can we tell it's ethanoic acid? Well, we have these 2 carbons in here, which means it's going to have the prefix eth. As well as that, we also have the kind of functional group, or like the kind of, the overall general structure of carboxylic acid. So in this case, we're going to have our OH down the bottom here and our double bonded oxygen up the top. So this is going to give us ethanoic acid. So in general, what's actually going to come about as a result of this oxidation of ethanol is that we're going to see ethanoic acid formed. So writing this out a little bit more formally, ethanoic acid is formed, and that's just the answer you're going to need to get here to get your full marks. So for this question, there was a total of 3 marks going, and in this case, those 3 marks were just associated for getting the term ethanoic acid right. There was a few other answers you could have had here, and because we're mixing several different reagents, you might have had a few different kind of resultant organic compounds formed. One of them would have been just the ethanoate ion, which is not going to have that extra oxygen bonded into it, as well as that sodium ethanoate would also be another acceptable answer here. So looking at part 4 here, what we're going to be working with yet again is Feeling's reagent. What we're told actually that Feeling's reagent itself is actually quite difficult to reduce. And from that, we're then asked another question, which is ethanol very easy or very difficult to oxidize? And in this case, we just need to come up with 1 or 2 of the answers. So it's a little bit of a 50-50 here. But yeah. So for this question, the required solution that will get you your full marks in this case is that ethanol is actually very easily oxidized, or you could just say easy to oxidize. So you kind of had a 50-50 here, and in this case, it was just that it's actually quite easy to oxidize. And for getting that, you would get a total of 3 marks. So having a look now at part 5, we're going to be asked to balance, or write a balanced half equation in this case, to show the reduction, so an important note there is reduction of the Cu2 plus ions of the Feeling's reagent in the test. So basically, we're actually given all the information that we need to know here, and the Cu2 plus ions is what's being reduced, and what we need to do is just write a very simple equation to show what's actually happening inside of the Feeling's reagent in the test. And thankfully, we don't actually need the Feeling's reagent formula itself. So in this case, what's actually going to happen is we're going to start out with our Cu2 plus, and recall back to our kind of shorthand way of remembering what's actually happening in reduction and oxidation, I guess. The term OILRIG comes to mind. In this case, it means oxidation is loss and reduction is gain, and this is in reference to electrons. So because we are reducing this Cu2 plus ions, it means we're actually going to be gaining electrons. So I'm going to just add on an electron here, and as a result, once we have that electron added on, and that Cu2 plus is actually going to, it's going to be reduced, this electron being added on, and what we're going to be left with is just a Cu plus. And this is actually the half reaction, or equation, should I say, that is actually needed to show the reduction of the Cu2 plus ions inside the Fehling's reagent. There was 3 marks associated with this question, and you needed to kind of get this full equation in order to get those 3 marks, and there wasn't any other way around it, unfortunately. But yeah, if you were able to recall this, a nice easy 3 marks. So moving now on to part 6 here, we're going to be given a little bit more information before we start this question. What we're being told is that ethanol is completely miscible with both of the aqueous oxidizing reagents mentioned above. And then we're asked to describe the polarity across the carbonyl group in ethanol. So basically what we need to do here is focus in on that carbonyl group in the ethanol and then talk about its polarity. So the little bit of information we're given beforehand isn't actually entirely necessary for this little this part here. You can actually just do it by assessing the polarity of the carbonyl group. So here's the required solution to this question, and let's just go through it first and kind of talk a little bit more about it. What we're being told here is that carbon actually carries a partial positive charge, whilst oxygen carries a partial negative charge. And this is really important to note when we're talking about polarity. So if you go to your the Linus Pauling table in your, or electronegativity table, should I say, in your log tables, what you'll find is that oxygen itself is going to be quite a small and very electronegatively dense atom, and this results in it being very electronegative. And as a result of this, it means it's going to carry that partial negative charge. And because it's carrying a partial negative charge, which I can just kind of show over here, this oxygen, which is just going to circle it in this purple color, it's going to carry that partial negative charge. It means that the carbon attached to it in the carbonyl group is going to carry that partial positive. And when we're talking about the polarity, in this case, it's just important to mention these. And while, you might necessarily go ahead and draw a little diagram like I have drawn over here on the right hand side, and personally I just find it a little bit easier to understand what's going on by drawing out what's happening. But in this case, the real takeaways is that carbon is partially positively charged as a result of the fact that oxygen is going to be partially negatively charged. And then this diagram also would be actually acceptable on its own because it kind of explains that you understand what's going on in terms of polarity when it comes to this group. So there's a total of 4 marks going for this question, and you got those 4 marks for talking about both the carbon and the oxygen, so you needed to include both. In this case, you got 2 marks for talking about the partial positive charge of the carbon, and you also got 2 more marks for talking about the partial negative charge of the oxygen. In this case as well, the diagram would completely suffice because we're showing those partial negatives and partial positives actually on the diagram. And finally, we're going to have a look now at part 7, which in this case is asking us to refer to the polarity across this carbonyl group to explain why ethanol is very soluble in water. So basically, the important thing to know here is that we're going to have to reassess that carbonyl group and use the answer that we get from, even just the previous question to explain why this polarity exists and why this results in the ethanol molecule itself being extremely soluble in water. So the required solution to get this fully correct in this case is going to be referring to hydrogen bonding. So whenever I start thinking about water and solubility in water in particular, I start thinking, right, well, let's think about what's happening. Is there any hydrogen bonding? What's the crack here? And in this case, hydrogen bonding is going to be present. And what we can see is that hydrogen bonding actually occurs between the partially negatively charged oxygen in the ethanol and the partially positive charged hydrogen as seen in the water. And what I'm going to do now is I'm going to also draw a small diagram to kind of reinforce this, but you could tackle it from a few different ways. Personally, the hydrogen bonding makes the most sense to me, talking about those partial charges, because we actually just mentioned them previously, but you could also talk about the attraction between them, but either way, it's kind of important that you include the partial positive and partial negative charges as an explanation to the solubility of it with water. And if you went down the diagram path, that would also be completely fine. So just drawing out our two molecules here, just on the left-hand side here is going to be our water molecule, and over here on the right-hand side we're going to have our the carbonyl group in the ethanol. And what we're going to see here is that the oxygens and the hydrogens in the water group is going to be, it's going to be a partial negative, partial positive kind of existence here, where the oxygen is going to carry that partial negative and the hydrogen is going to carry that partial positive. And this is going to result in a hydrogen bond forming between these hydrogens in the water, these partial hydrogens, these charges, I should say, the hydrogens, the partial positive charges, and the oxygen in the carbonyl group, which is just up here, should I say, with that partial negative charge, which we can see in the carbonyl group of the ethanol. And yeah, either way, however you want to approach this question, as long as you're including the diagrams, as long as you're including those partial positive, partial negative charges and explaining the presence of these hydrogen bonds, you get your full marks. In this case, there was a total of 3 marks going, and as I was saying earlier, those 3 marks can be given out for just doing the diagram, or also this answer, including everything we've already said. So having a look now at part C, in part I, we're going to be asked here to explain the term activation energy. And this is going to be because the question that we're going to be working on here is going to be related to rates of change, things like concentration and stuff like that. And a big part of that is going to be activation energy. So this is just going to be a straightforward definition. So yeah, let's get straight into it. So the answer for this question is going to have 2 main parts, and the first one is going to be talking about energy, and in this case activation energy is going to be the minimum combined energy of colliding particles. That's going to be your first part, and then the second part is going to be, for this actual reaction to take place. So basically activation energy is going to be the minimum combined energy of the colliding particles needed for a reaction to take place. By including both of these terms, you're going to get a total of 4 marks, 2 marks going to each of them. So you get 2 marks for saying minimum combined energy of the colliding particles, and also you get 2 more marks for mentioning the fact that this is what's needed for the reaction itself to take place. And you could also kind of dress this up by saying, instead of reaction to take place, you could also say for an effective collision to take place, or something along those lines. But either way, it's important to include both of these in order to get your full marks. So having a look at part 2 now of C, we're going to be working with a diagram in this case. And what we're told is that the reaction profile diagram for the reaction X to Y with and without a catalyst C is shown below, and we're going to have a look at that in a minute. And basically what we're being asked is, what is the value of EA, or the activation energy, for this reaction without the catalyst? So it's important to note that we're being asked what is the activation energy for this reaction without the catalyst. So having a look now at our diagram, what we can see is that there's going to be a graph, and there's also going to be another one with like a kind of like a dotted line. And in this case, we're told that the reaction without the catalyst is going to be the solid line, and the reaction with the dotted line is going to be with the catalyst. And in this case, we're being asked about the one without the catalyst. So we're going to be focusing on the activation energy for the solid line. And in this case, if we just kind of look at our diagram here, what you'll be able to do is you'll be able to see the answer. So your first instinct here might be to just look at the kind of height of the curve in the middle here. Like, you might be immediately drawn to this height here and go, right, well, this is the energy needed to reach the top, so this must be the answer. It's going to be 120. Well, that's actually wrong. And the reason that's wrong is because the activation energy is going to be the difference between that peak but also where we kind of started from. So we're going from X to Y, so that is actually going to be the same as this height here. This is going to be our activation energy, just to draw the arrow in right now. So it's actually going to be the difference between that peak, which is going to be 120, and our lower X, which is going to be 20 here, and this is just going to be measured in kilojoules per mole. So the answer for this question in particular is just going to be 100 kilojoules per mole is going to equal to this activation energy. And for getting this right, you're going to get a total of 3 marks, and that was just kind of getting the right answer here, 100 kilojoules per mole. So now let's take a look at part 3. And in this case, part 3 is going to be yet again referring to the diagram. We're going to be asked, by how much does catalyst C lower the value of EA? So the activation energy, should I say. And in this case, it's important to know that we're not being asked for the activation energy for the catalyst. Now we're asked about the difference. By how much does the catalyst lower that value? So it's important now that we go and find out what the activation energy is for the reaction with the catalyst, and then compare that versus that with energy of the reaction when it didn't have the catalyst, and then get our difference there, which will be the answer in this case. So as we said before, the activation energy without the catalyst, which I'm just going to write this in, so without C is going to equal to what we said earlier was 100 kilojoules per mole. And what we have to do is do the same process again to find the activation energy. So writing that down again here, activation energy with the catalyst. And then what we can do is go ahead and find that difference. So the difference here is going to be yet again between this peak of the dotted line and X here, which is going to be this kind of area, or should I say this height here. And what you'll find is that that is going to be 60 kilojoules per mole. And then once again, what we're being asked here in this case is to find the difference. So what we're going to do is find the difference between these two and subtract them away from each other. What you're going to find is 100 minus 60 is going to be 40 kilojoules per mole is going to give us our correct answer. And for getting this correct, you're going to get a total of 3 marks, which is just associated with getting that correct final answer. So now that we have finished part 3, we're going to be moving on now to part 4. And in part 4, we're asked to find the value of delta H for the reverse reaction of Y to X. So now we're going from Y to X, not X to Y. So that's an important thing to note. And in this case, delta H refers to the difference in the energies here between X and between Y. But it's important now that we pay very close attention to which way the reaction is going. So once again, referring back to our diagram, in this case, we need to identify first what is delta H. And delta H, as I was saying earlier, is going to be the difference between, the energies of X and Y. So this is here is actually going to be delta H. So writing that down, this is going to be delta H. And to write this down, just kind of eyeballing it here, what is delta H normally? And then we can go ahead and start worrying about the reaction. So what's going to happen here is X here is going to be at 20, and now we need to determine what Y is at. So Y is at just about halfway between 60 and 40, which means it's going to be 50 here. So delta H is going to be that difference between the two of them. So it's going to be a difference of plus 30, which is going to equal to delta H. And this is going to be for X to Y. So this is just going the normal way. Note, however, that we were actually asked for the other way. So the important thing to note is that if we're going from X to Y in this case, what we've already identified is that the change here, delta H, is going to be plus 30. But if we're going the other way, actually, what you're going to notice is that Y is actually going to drop down. So it means that what's going to happen is the sign in front is going to change, but the amount is actually not going to change. So what we're going to see here is that the answer is going to be minus 30 is going to equal to delta H, but this is going to be for Y going towards X. And that's actually the answer that we wanted to find. So in this case, it's going to be, and I'll just write it down here, it's going to be minus 30, and this is measured in kilojoules per mole, don't forget. So yeah, yet again, a nice simple kind of just a bit of eyeballing off the graph. And in this case, you're going to get 3 marks for getting this answer correct. So now that we have finished all of the graph work, we can now move on to the final part of question C, and in this case it's going to be part 5. And we're given this big paragraph of information at the top, so let's go and have a read through it first. And what we're told is that the reaction between pure hydrogen and oxygen gas mixed in the ratio of 2:1 by volume and forming water is actually very slow at room temperature. So that's the first thing to note. But we're told then that it's actually very rapid, should I say, when a little powdered platinum catalyst is added. And then we're told that this is an example of and sorry, your line, we'll just do it again here, a heterogeneous catalysis, should I say. And what we're being asked here in part 5 is to actually explain this underlying term. So what is heterogeneous catalysis? And in this case, the answer required to get you your full marks is that heterogeneous catalysis is actually, as a catalyst, should I say, that is in a different phase from the reactants and the products. So that's an important thing to note here. And basically what that means is, when I say different phase, it could be a water or liquid or, I'm sorry, not water or liquid, a liquid or gas or a solid. But basically, let's say if your catalyst is going to be a solid, then, your hydrogen, oxygen are gases. So if you just look at this example here, what we're told is that we're mixing hydrogen and oxygen gases here. So that's one, they're going to be gases. And this is going to be mixed, in an area or in a container with a little bit of powdered platinum catalyst, which is a solid. So they're going to be different states, if you will. And in this case, a heterogeneous catalyst is one that is in a different phase from its reactants and products. And this is kind of easy to remember because this hetero, should I say, prefix is kind of going to give that all away. So heterogeneous in this case means different from, so like a heterogeneous is going to be like kind of different. So that's why we have this term different. So different phase from the reactants and the products. And by getting this correct, you get your total of 3 marks, and you need to include the fact that they are in different phases from the reactants and products, the catalyst that is. Ultimately, now we're going to move on to the final part, which in this case is part 6. And we're asked to describe the mechanism by which the catalyst increases the rate of this reaction. Now, there's actually two different theories for catalysts. One is the intermediate theory of catalysts, where an intermediate is formed, and the other one is surface absorption. So we're going to have a look at the surface absorption one first, and then I'm probably just going to touch on the other one, but personally I would go for the surface absorption one because it makes a little bit more sense to me. So in this solution, what we're going to see is the surface absorption theory of catalysts. And the first thing to note is that a catalyst is going to increase the rate of reaction as reactants are adsorbed or bond with the surface of the catalyst, and the reaction takes place on this surface. So that's the first thing to note. Basically, what's happening is the reactants themselves are going to bond with the surface of this catalyst, and this is actually where the reaction itself is going to take place. So an example of this would be in the previous question when we're looking at the powder platinum catalyst. That would be the surface of the powder platinum is actually where the reaction is going to take place. And then moving on from there, what we're going to see is that the bonds actually within the reactant molecule, they're going to break down. And as a result of that, as they break down, the activation energy is going to be lowered overall. So that's an important thing to take away. Moving on from that, once the activation energy has been lowered and the molecule has kind of broken down a wee bit, the products then go ahead and leave the surface of the catalyst. And if you want to kind of continue on a wee bit longer, they go ahead and form whatever molecule is needed after the fact. So the important takeaways from this is that the reactants themselves are absorbed onto the surface, or even if you want to phrase it as occupying active sites on the catalyst. And then what's going to go ahead and happen following this is that the bonds within the molecule are going to weaken, they're going to break, and what you're going to see is that the activation energy is going to be lowered. And then following this, what's going to happen is they're going to, leave the surface, and then they're going to go ahead and form, whatever they're going to go and form. So in this case, there was a total of 9 marks going, and the breakdown was as follows. You got 6 marks for getting your first point correct. So the first point that we're kind of going for in this case is that they're going to, it is actually in this first paragraph, it's that they're going to bond with the surface, and actually, the reaction itself takes place in the surface. That's going to be the first point. And the second point, and we've actually got a couple of ones in the second paragraph, but the first one that I went with, I guess, in this case, is that the bonds are going to, inside the reactant molecule, they're going to break down. And that's like another thing to note. They're going to weaken, they're going to break, they're going to stretch. That's something else that you want to include. And also including kind of the thing I was saying here about the activation energy being lowered overall, and then the product leaving, that also would get you marks. But in this case, you only really need 2 points, and I've kind of given more than that in this case. As well as that, we're going to just touch on the intermediate theory for catalysts. It's basically kind of a similar idea, but in this case, an intermediate is formed. So if you included anything like that in that second paragraph, for example, that would also get you your full marks. So finally, we get to move on now to Part D. And Part D itself is going to actually have 2 subparts, because Part D actually asks us questions about some of the optional sections of the course that you'll cover towards the end, hopefully, things like atmospheric chemistry and metals and that type of thing, and crystals as well sometimes. And in this case, we're going to be looking at Part A, and then we'll move on to Part B. So Part A is going to be some questions on, I believe it's atmospheric chemistry, just kind of glancing at it here. And in this case, we're given a paragraph. So the paragraph is saying, ozone is formed, should I say, and broken down by photodissociation, which is underlined, I'll just underline it again, in the stratosphere. And we're told that CFCs in this atmosphere were identified as a major contributor to damaging the ozone layer, and their phasing out was agreed internationally. And basically what we're asked to do in Part I is to explain this underlined term, which in this case is photodissociation. So photodissociation itself is actually defined as the breakup or the decomposing of something using, or by the use of, I guess, UV light in this case. So basically you could say that it's the breaking up or splitting up even of, whatever it is in this case, via the use of UV light, or electromagnetic radiation also would work in this case. So just kind of a straightforward definition, and it has 2 parts in it, which is the first one being the breakup, and then the second one, which is how it's actually being done, which in this case is the use of light. And for getting this correct, you get a total of 8 marks. You're getting your first 4 from correctly identifying, saying breakup or splitting up or the decomposition of. And then you got your other 4 marks for mentioning the process by which it's done, which is by the use of light or UV or electromagnetic radiation. All of these are completely acceptable. Moving now on to Part 2, here we're going to be asked, write a balanced equation for the photodissociation of ozone in the stratosphere. So what we have to do here is write down First of all, we're going to start out with our ozone. So ozone is actually O3, and what's actually going to happen is it's going to photodissociate. So we're going to have an arrow here. I'm just going to write above it, I'm just going to write UV. So basically, once we, shine this UV light on it, what's going to happen? And basically, what's going to actually happen is the UV light is going to cause this ozone to be broken up into an O2, which is something that we're nice and familiar with, and also an O on its own. And as well as it's just going to have this little dot up here. Now, just to talk a little bit more about what this dot up here means, this is what we call it's a radical, or a free radical, if you will, and they're extremely reactive because they're kind of on their own and they really need to get stable, and they will react kind of with whatever's around them. But in this case, this is the required balanced equation to give you the photodissociation of ozone into oxygen, O2, and the oxygen free radical itself. And for getting this, you would get a total of 3 marks, and it was just you just kind of needed to know the formula of, in this case, or like kind of the breakdown of it, which is, as we can see here on the screen. So moving now on to part 3, here we're asked to state one major use for CFCs before the Montreal Protocol. And what I'm going to do here is write down the one that comes to mind every time when I'm thinking about CFCs and what they were used for, and then we'll have a look at a few of the other major uses for them. So to me, the major use for CFCs was in the gas for aerosols. And when I think of CFCs, funnily enough, the first thing that comes to mind is hairspray. And the gas for those aerosols, for things like hairspray and deodorant in some cases, that gas was actually a CFC, which is obviously not very good for the ozone layer. A few other answers you could have had here are things like the gas in refrigerators, or fridges, I guess, freezers, air conditioning units, as well as that you could also talk about things like the gas in fire extinguishers. This is all, at the time, was all made of CFC gases, which was really bad. But yeah, for this, you got a massive 6 marks if you got this right, which is a really nice thing because, I mean, for one line, yet again, 6 marks is absolutely huge. So having a look now at part 4, we're going to be asked to show by means of balanced equations the photodissociation of the molecule CCl3F, giving a chlorine free radical, and how chlorine free radicals break down ozone in this chain reaction kind of way. So basically, we're going to be writing down a few balanced reactions here, balanced equations, if you will, for the photodissociation of CCl3F. So the first one that we're going to see here is we're going to start with our CCl3F, and what's going to happen is once we have this shining in the UV, or shine UV light on it, it's actually going to dissociate into the following, which is going to be CCl2F, and this is going to be a radical because we're actually removing one of those chlorines, so it's actually no longer stable, and we're going to also have another chlorine free radical over here. Now what's going to happen is, in this question we're actually asked to show the photodissociation of it, but we're also asked to show how does the chlorine free radicals break down the ozone layer. So that's the next step that I'm going to do now. And what we're going to see is that oxygen, or should I say that O3, which is our ozone, is going to mix with that, react with that chlorine free radical, and what's going to happen is once they react, we're going to see that it's going to go ahead and form O2 and ClO free radicals as well. Now you might be wondering where I'm going with this. The next step that we need to include in this is kind of the chain reaction part of this question, which is that ClO free radical itself is going to mix with some of the oxygen free radicals to go ahead and this is going to go ahead and form a little bit of oxygen itself again and another chlorine free radical, just to make this a bit cleaner. And the reason that we were mentioning the chain reaction part of it is because what you can see is that we're getting back, a lot of the same stuff over and over again. We're getting a chlorine down the bottom, a chlorine free radical down the bottom here. We're also getting one up here. So basically what's happening is these reactions are occurring all the time, and they're creating chlorine free radicals, which are reacting with ozone. But at the very end of the reaction, more chlorine free radicals are created, which, react with ozone again. And basically this causes that deterioration of the ozone layer, which was mentioned before. So a total of 6 marks going here, and that was broken down evenly between these 3 equations. So you got 2 marks for getting each of these right. So 2 marks there, 2 marks there, and 2 marks there. And what you can do, just kind of visually, you can verify that these are all balanced. Look at this, for example, this top equation here. What you'll find is on the left there is 1 carbon, on the right there's 1 carbon, on the left there's 3 chlorines, on the right there's 3 chlorines, albeit one of them is now a free radical. And then on the left there's 1 fluorine, and on the right there's 1 fluorine. And you can repeat this process going down. These are all nice and easy balanced equations. So finally, we're going to be moving on to the last part of, like the first part, I guess, of D, which is kind of confusing in its own right, but this is going to be part 5. And in this, we're actually asked to explain, yet again, using a balanced equation, how the presence of methane in the atmosphere can help absorb chlorine-free radicals. So this is going to start out with another equation, and I'm just going to kind of start this with the information that we know. So we're actually being told here that we're going to have methane in the atmosphere. So it's going to be CH4, which is going to be our chemical kind of formula for methane. And what's actually going to be happening is it's going to be absorbing chlorine-free radicals. What we're going to be adding here is a chlorine-free radical here. So now we have to see what's going to happen once these two things react. And what's going to happen is actually one of the hydrogens on the methane is going to be ripped off. And that's going to leave us with a methyl free radical, so CH3 with a little dot up there, meaning it's very unstable and it's a free radical. And that hydrogen that was ripped away from the chlorine, or the methane, should I say, is now going to go ahead and bond with the chlorine. So what we're going to get left with is the hydrogen bonding with the chlorine to give us HCl, which is quite familiar to us at this stage. So this reaction here is going to show that actually by adding methane, what's going to happen is all of those chlorine-free radicals, which we see over here on the left-hand side, are going to come together and actually be absorbed out of the atmosphere because there's no chlorine-free radicals over here on the right-hand side, which is exactly kind of what the purpose of adding methane to the atmosphere is. But either way, yeah, it does kind of help with the reduction of chlorine-free radicals. So for this question, there was a total of 2 marks going, and those 2 marks are just going for balancing the equation correctly. In this case, it was not too bad, and yeah, that is kind of all of the questions in part A. So moving now on to part B, since we finished part A. Part B now is going to be another part of like the optional section of the course, and in this case we're going to be looking at kind of electrochemicals and kind of that type of stuff, and in this case it's going to be we're going to be given this paragraph that we're going to read through, and then we're going to be moving on to part I in this case. So what we're being told here is that electrochemical reactions are involved in the corrosion of metals, in corrosion prevention, and in the extraction of metals from their salts. And then we're told a little bit about galvanizing, and then we're asked explain how galvanizing actually protects an iron object from corrosion even when the zinc coat is scratched. This is going to be like a paragraph answer. It's just going to be like a few words. In this case, it's going to be no balancing equations or anything like that. So let's get straight into that. So in this case, galvanizing actually protects an iron object when coated in zinc, as zinc is actually higher up the electrochemical series. So basically, as a result of the zinc actually being higher up the electrochemical series, it means that the zinc itself is actually oxidized much easier than that of the iron, and this is going to, protect the iron object from any form of corrosion. So there's a few different ways you could approach this answer. I went for talking about the electrochemical series and the fact that zinc is going to be higher up on that, as well as this resulting in the fact that zinc is more easily oxidized. But you could also do kind of the opposite, which is saying that iron is more electronegative than the zinc. Either way, by just kind of including the fact that the electrochemical series is involved and where zinc and iron on it, and how this kind of results in the protection of the iron object, would get you your full marks. So in this case, there was 3 marks going, and in order to get those 3 marks, you needed to say how zinc was higher up that electrochemical series and therefore was more easily oxidized than that of the iron. Moving now on to part 2 here, we're going to be told about sacrificial anodes, and then we're going to be asked to identify a metal that is often used to make these sacrificial anodes. And in this case, what you're going to be looking for is something that is very easily oxidized to make these anodes. And you have a few choices, but I'm going to give you my main one now. So in this case, the metal that I've gone for is zinc. Now there's a few other options you could have gone for. As I was saying, you're looking for metals that are high up on that electrochemical series, should I say. So you could have also gone for something like aluminium, or another option you could have gone for is magnesium. But either way, including any of these 3 answers would have gotten your full marks. And speaking of full marks, there was 3 marks going for this. In this case, you just need to include the name of the element in order to get them. So looking now at part 3 here, we're going to be asked, how does a sacrificial anode actually help protect a steel hull of a ship from rusting? So basically, we're going to be asked now, what's actually the point of these sacrificial anodes, and how do they protect everyday things such as a steel hull of a ship? How does it actually protect it from rusting? So in this case, the required answer is that the metal used in the sacrificial anode is actually going to be higher up on the electrochemical series. So that's an important thing to note. And it's going to be higher up in that electrochemical series than the metal in the ship's hull. And as a result of this, it means that the anode is going to be, this sacrificial anode, should I say, is going to oxidize significantly more easily than that of what the ship is. And this is going to result in the ship's hull actually being, prevented from rusting, which is obviously kind of the overall goal of the sacrificial anode. Now, there's a few different ways you could approach this. As we were saying earlier on, we were mentioning that sacrificial anode has to be higher up in the electrochemical series, but you could also say that it's more easily oxidized, it corrodes first before that of the iron, that's sacrificial anode once again, or it's more electropositive, which would be another correct answer. Either way, making sure to include these buzz terms will help you get your full marks in this question. So for getting the full marks in this question, you'd be getting 3 marks, and those 3 marks, as I was saying earlier, are really kind of just associated with mentioning the electrochemical series and the fact that the sacrificial anode, the material that's made of, the metal, should be higher up on that than that of the steel hull. And you could also talk about oxidizing, which would also get you full marks, but it's not, you don't need to include both of them. I just include both of them just to make it a little bit more clear about where I'm coming from on this. So moving now on to part 4 here, we're going to be asked a question about anodized aluminium. And in this case, we're being told that it is more resistant to corrosion than just standard aluminium. And then we're being asked actually, what is anodized aluminium? So yet again, this is just going to be a straightforward definition about what anodized aluminium is. So anodized aluminium is not too dissimilar from that of the kind of like the process of galvanizing something, because it protects the metal a little bit more from corrosion and the outside elements. But in this case, anodized aluminium has an aluminium oxide coat on the surface. That's like the kind of the key takeaway. Now, instead of saying aluminium oxide, you also could have said Al2O3, which is just the chemical way of saying it. But in this case, it's important to note that it's actually like a coat of this aluminium oxide on top of the original aluminium, which is going to make it a little bit more resistant to that corrosion. So having a look now at part 5 here, we're going to be given a diagram now. I just don't have it right here and right now, but I'm going to have a look at it in a moment. And this diagram is going to show an arrangement for carrying out the electrolysis of some molten lead bromide using these inert electrodes, and it's also going to be done so in a fume cupboard. And we're going to be asked a question which is going to be about writing half equations, in this case balanced half equations, for the reactions that occur at the 2 electrodes. So what I'm going to do is pull up that diagram now, and we're going to have a look at it and then begin to write down our half equations that are required to get your full marks here. So here on the left hand side, we have our diagram, which is going to show the electrolysis of that molten lead bromide. And what's going to be happening here is we're going to need to write the 2 equations that are needed for the electrodes, 2 half equations. And just to write down the formula now for the lead bromide, it's going to be PBB or 2, which is going to be lead, and then we're going to have 2 bromines in there as well. So what we're going to be doing here is looking at the first half reaction, which in this case is going to be our lead, which is going to have a 2+ charge here, and it's going to be 2 electrons going to be added on here. And this is because it's going to be reduced. And when we're reducing, according to OILRIG, it's going to be oxidation is loss, reduction is gain. We're gaining 2 electrons here, and that means that we're adding those 2 electrons onto the lead in this case. And once we add those 2 electrons onto the lead, what you're going to see is that 2+ charge is going to be cancelled out quite nicely, giving us just good old lead on its own, completely neutral in this case. And now looking at the other electrode, what we're going to be left with is so just kind of having a look at the oxidation numbers. In this case, lead is going to carry a +2 oxidation number, or +2 charge, I guess, in this case. And overall, the molecule is going to have a neutral charge, which means that these bromines are each going to have -2 between them, and it means that individually they're going to have -1. So what we're going to do is look at just an individual bromine. So what we're going to have is a bromine, which is going to have a minus charge here. And what's going to happen here is this is going to change into just Br plus an electron. Now, it's important to note that you could have here bromine, just kind of here, bromine and then minus an electron, but that's kind of just not the way we do things. I guess it's just always you want to have a plus electron because it's a bit just for syntax and stuff. So that's why we have it as it is, with the Br minus goes to Br plus that electron. And these are the 2 half equations required to get your full marks. In this case, there's a total of 8 marks going here. You got 4 for each, so you got 2 marks for getting the formula correct, and 2 marks as well for getting the balancing. And similarly for this one, you're going to have 2 for the formula and 2 more for balancing, and that gives you your full 8 marks. So now having a look at part 6 here, what we're going to see is the question is going to be asking us, how is charge actually transmitted through the molten PB or lead bromide in this case? So this is just going to be a straight kind of answer, and what I'm going to do is just write that down now. So the required solution here to get you your full marks in this case is going to be that the charge is actually going to be transmitted by the movement of ions. And if you wanted to specify what ions are going to be looked at in this case, what you're going to see is that there's going to be lead ions, so that Pb2 plus that we were looking at earlier, and also our individual bromine ions, so Br minus in this case. And basically, yeah, that charge is going to be moved around by the ions themselves, and you could have wrote down either of them in this case, but you know, the important term here is that movement of ions. If you're getting that right, you get a total of 2 marks, and those 2 marks are just associated for getting the term movement of ions right. Here I'm just specifying which ones, which ions are in this case, but it's really important that you just include the term movement of ions.